All right, so I know it's labeled lesson number two, but just disregard that. All right, now basic chemistry. We're gonna start with that. Some units that you should maybe remember when you took chemistry regions. A mole is a unit that represents essentially a quantifiable amount, a pile of particles, atoms, molecules, and it can be weighed in grams. When we refer to the gram formula mass or gram molecular mass, they both mean the same thing. This represents the amount of grams of a mole of a certain substance, a certain element, a certain compound, a certain molecule. Now, the volume of a mole of a certain substance can also be measured in liters, but that is for gases only. And at STP, which is standard temperature and pressure, 1 mole of any gas is 22.4 liters of volume. I will elaborate later on specifically on what STP means. Now, 1 mole is also equal to 6.02 times 10 to the 23 molecules. Now, it may seem a little bit small just because it's in scientific notation, but that is a huge number. And that's essentially the number of molecules that is in 1 mole of a certain substance, no matter whether or not it's a gas, a solid, or a liquid. And this number has been coined as Avogadro's number. You should remember some of this from Regents chemistry, if I'm not familiar, if I'm familiar with the material in Regents Chem. Uh, let's see. Expressions of concentration. So these will be used for a specific chemical solution. A solution has a solute and a solvent. A solute is essentially uh, let's say you had a bowl of soup, right? And you wanted to add salt into it. The salt would be the solute and the solvent would be the liquid of the soup itself. Now, in order to represent this, we have these 5 units. Molarity, which is the most important one that we should be focusing on today, because it is also very much heavily used in the equilibrium aspect of chemistry. Now, molarity is represented with a capital M, and this is the moles of the solute. So if you had salt, let's say table salt, NaCl, sodium chloride, that will you take the number of moles of sodium chloride and you divide this by the volume of whatever solution that you have, let's say soup. And so let's say I had 2 moles of sodium chloride inside a 2-liter solution of soup. That would mean that the molarity of sodium chloride in this soup would be 1 molar. Now, molality is similar, but rather than dealing with the volume of the solution, it deals with the mass of the solvent. So it's still moles of solute. It's still the same sodium chloride that is being added, but now instead of dealing with the whole solution, which includes both the solute and the solvent, sodium chloride and the liquid, the solvent deals just with the liquid aspect and it only deals with the weight of it. And molality is represented in the moles per 1 kilogram of a certain solvent. And this is represented with a lowercase m rather than a capital M. You won't see molality too much since it's not that much of a common unit when it comes to testing. Now let's go with the third unit, percent by mass. Now, percent by mass and percent by volume are pretty similar, but instead of mass, it's volume. And the way you calculate it is you take the mass of the solute and you divide it by the mass of the solution. And you take all that and multiply it by 100 in order to get a percentage of whatever solute you added into a solution. Now, using the example from before, it would be me taking 5 grams of sodium chloride into a maybe 100 gram in totality solution. Now that 100 grams, it includes both the sodium chloride and the water that I added to said soup. And then I would multiply that proportion by 100 in order to get the percent by mass. Now the same case is for percent by volume, but rather than 5 grams of sodium chloride, let's say it's, I don't know, 5 milliliters of the solute. Now, the thing with percent by mass and percent by volume is that you aren't limited to liter or kilogram. You can use any units of volume and mass as long as if in your calculation you use the same unit for both. Now, the last unit is parts per million. This is similar to percent mass by volume, but now instead of multiplying by 100, you multiply by 10 to the 6th power, aka 1 million. And parts per million is mainly used for uh, substances that are added to a solution that are very small in concentration. So it would be maybe 5 times 10 to the negative 6% in percent by uh, mass, but when it comes to parts per million, it turns out to something like, I don't know, 5 or 50. I can't do the conversion off the top of my head. Now let's move on to the next slide. This is standard temperature and pressure, aka STP. You're going to see this a lot. And what this refers to is essentially a standard set of conditions for temperature and pressure of a certain environment where a chemical reaction is being analyzed or something of that nature. Now, for temperature, the standard temperature is 273 Kelvin, 0 degrees Celsius, or 32 degrees Fahrenheit. Now, you might recognize the last two, 0 degrees Celsius and 32 degrees Fahrenheit, because that's the freezing point of water. But 273 Kelvin, if you don't remember Regents chemistry too well, that's okay. Kelvin is just another unit of measurement. It is incrementally structured similar to Celsius, but it is only greater by 273 units instead. So if I had, let's say, 25 degrees Celsius, I would add 25 degrees Celsius to 273, and that would get me Kelvin. I did make a mistake on the slides here. It should say K equals degrees Celsius plus 273. My mistake. Please disregard what's on the slide for that matter. That degree Celsius formula, I believe, is still correct, though. The degree Celsius can also be determined by 509 times the degrees Fahrenheit minus 32. Now, that second formula, you really won't see much. Most chemistry problems you'll see will either be using degrees Celsius or Kelvin. Just be sure that when you are doing any calculations that you use Kelvin, because for most formulas, they only work with Kelvin and not so much degrees Celsius. Now, standard pressure. This is something that I hope you don't remember. I hope you do remember, but it's okay if you don't. Now, the standard pressure unit is 760 milligrams, millimeters of mercury, not milligrams, I apologize, or 760 torr, or 101.3 kilopascals, or 1 atm, aka 1 atmosphere. Now, with this conversion, 1 millimeter of mercury is equal to 1 torr. And if you want to convert to any other units, you simply use the proportion of whatever two units you want to compare. So if I was doing conversion from millimeter of mercury to ATM, I would use dimensional analysis and just set whatever proportion I want equal to 760 milligrams of millimeters of mercury over 1 atm or 1 atmosphere. Now, I will elaborate further on the aspects of pressure later on. Now, let's talk about gas stoichiometry. Now, the kinetic molecular theory of gases is specifically for ideal gases. Now, ideal gases, they consist of small, tiny particles. They are far apart. They have a bunch of empty space between them, which will mean that their volume is essentially negligible. They have no volume. And the particles within the gas travel in random straight line motions. They don't travel curved, it's only straight line motions. And the collisions between these gas particles are elastic. And essentially what elastic particles mean is that these particles, they separate after they collide and they don't have a change in momentum or kinetic energy. And we can see that these collisions are elastic through any observations that we make because when gases are in a room, there is not a temperature change. The gases don't suddenly change temperature when they're in a room, despite them colliding. Now, at a given temperature, the average kinetic energy remains constant, and also lighter gases will diffuse faster than heavier gases. I will elaborate on this later. There is a law that deals with this principle, and there are no forces of attraction or repulsion between ideal gas particles. Now, ideal gases are given the name ideal because they don't essentially, they rarely are found commonly in the real world. What is found in the real world are real gases. Now, real gases differ from ideal gases because rather than not having a volume, they do have a volume that is not negligible. And gas particles, they also have weak forces of attraction to one another. If you notice earlier, I mentioned that ideal gases, they have Yeah, in number nine, no force of attraction, and number four, gas and no volume. But real gases, they do occupy a small volume that is not negligible. You can't disregard it in any actual calculations when you want to be accurate. Now, in order for real gases to be more ideal, we can set up experiments at a higher temperature and a lower pressure. Now, what this will do is it will create an environment for the gases where there's more empty space, so it can make the volume more negligible, which will make it behave more like an ideal gas. Now, air pressure. Uh, when I mentioned STP, uh, I refer to millimeters mercury, specifically 760 millimeters mercury, or Hg. That is the symbol for mercury. I refer to this because the tool on the right that you can see, this was used to essentially determine a certain atmospheric pressure using this early time barometer that I was able to find a picture of. Now, the way this works is that the atmospheric pressure will act on a pool of mercury. And from there, the mercury will travel up that tube that you see in the diagram because the atmospheric pressure was applying pressure to the exposed mercury. And from there, the distance that the mercury traveled up the glass tube was referred to as the pressure of the atmosphere. And now, so that means if the atmospheric pressure was greater in one certain region, that would mean that the mercury would travel further up the tube and would travel a greater distance than, let's say, 760 millimeters mercury. And those are the other units I mentioned earlier for standard pressure. You're going to see STP a lot in any problems that you're doing. And here is a manometer. Similar to the barometer that I've shown in this slide, this manometer can also be used to measure pressure. Now, in this case, the manometer can be used to measure the pressure of a certain gas against the pressure of an atmosphere if the P with the subscript of 0 were open-ended. It would mean that the atmospheric pressure would act on that liquid that is inside, that mercury, liquid mercury. And from there, in diagram 1, you can see that on the right side, the right-hand side, the mercury is higher up. This means that the pressure of the gas is acting against the mercury more so than the pressure of the atmosphere. This means that we can figure out the pressure of the gas if we know the pressure of the atmosphere, because we could take that pressure of the atmosphere and then we can add that difference between the pressure of the gas, that level where it says X right there, and the level where it says Y, that line right there, we can subtract that difference in height, which is labeled as H centimeters, and this can be used to find the pressure of the gas that is inside the manometer. Now, in diagram 2, these two levels of mercury are the same. This means that the pressure of the gas and the pressure of the atmosphere are both equally acting on the mercury. In diagram 3, you can see that the pressure of gas is much less than the pressure of the atmosphere because the pressure of the atmosphere is pushing that mercury further down into the manometer. And this difference in height between the mercury can be used to find the pressure of the gas, as long as if you know the pressure of the atmosphere. You can take the pressure of the atmosphere and subtract it by that difference in height of the mercury. And from there, you can figure out the pressure of the gas. Now, another topic that we need to cover is vapor pressure. Now, when the temperature of a certain environment increases, the kinetic energy of the vapor that is produced by a liquid will also increase. And because of this, it will lead to an increase in evaporation and vapor pressure. This is how boiling liquid works. The liquid is heated, right? If you're heating a kettle for, I don't know, maybe some tea, then the vapor is produced, the steam that you see. That's the water vapor that you see. And when this vapor pressure is equal to the atmospheric pressure, that is when liquids will evaporate and boil. Now, at a higher altitude, let's say you were uh, mountain climbing or hiking, the atmospheric pressure is lower as you reach an increased altitude. And because of that, that means that it doesn't take as much vapor pressure for a liquid to start boiling. And that means that there's a decreased boiling point. What decreased boiling point means is just the temperature at which a liquid will boil. And that boiling point will be decreased at a high altitude because the atmospheric pressure is so much lower. Now, the nature of liquid. This is very important. Disregard the colors, just focus on the number of dots and essentially the density of the dots that you see. Now, in these diagrams, the liquids are represented on the bottom in a certain container. Now on the left, all the circles with all the gray, this has a strong IMF. IMF refers to the intermolecular forces of attraction between the molecules within the liquid. Now, there is intermolecular and intramolecular. I won't be covering what those specifically mean, but I can give a general overview. Now, IMF, intermolecular forces of attraction, they deal with the force of attraction between specific molecules. Now, intramolecular goes on an even deeper level, an even more microscopic level, because intramolecular deals with the bonds and the forces of attraction between specific atoms. So let's use water as an example. The intramolecular forces of attraction are between the hydrogen atom and the oxygen atom in water. But the intermolecular forces of attraction deal with the force of attraction between specific water molecules, specific H2O, H2O molecules. The attraction between these two molecules is referred to as the intermolecular forces of attraction. Now, when there are stronger forces of attraction, it means that it's hard to separate them into a gas. That means that it's going to take more energy, and you're going to need to raise the temperature more in order to make these liquids evaporate or boil, hence the higher boiling point. Now, if you look on the image to the right where it's all blue, you can see that this has a weak intermolecular forces of attraction. That means that it should be very easy to separate these molecules out and turn them from a liquid into a gas. And that means that it'll take less energy, which means you don't need as high of a boiling point in order to make these particles start to evaporate. Now, when certain compounds and molecules have a weak intermolecular force of attraction, they are considered volatile substances. And volatile essentially is just a term that has been used to describe these liquids that are able to evaporate very easily. Now, this diagram, I'm sure you recognize is from the chemistry Regents reference table. And from there, you can see propanone, ethanol, water, and ethanoic acid. Now, if we look at 100 degrees Celsius at standard pressure, that is where the boiling point of water is commonly. Ugh. Now, let's compare water with, say, propanone. At the standard pressure, which is 101.3 kilopascals, the boiling point of propanone is somewhere around 55, 56 degrees Celsius versus water's 100 degrees Celsius. Now, this means that propanone is a more volatile liquid.